The dominant theory among the majority of scientists is that the current explanations regarding the origins of the universe remain the leading interpretation of its early development. This hypothesis links the creation of stars and planets, which ultimately led to the emergence of life, including human beings. Despite its unusual title, the Big Bang provides a comprehensive view of what might have occurred at the universe's dawn. In the beginning, the universe was concentrated in an extremely tiny space, far smaller than the head of a pin, packed with particles. From this densely packed state, a colossal release of energy and matter, known as the Big Bang, occurred. This cataclysmic event, which took place billions of years ago, set in motion the expansive history of the universe. As scientific understanding advances, however, discrepancies have started to arise, calling into question the assumptions of this theory. When NASA launched the James Webb Space Telescope, JWST, the largest and most advanced space observatory ever built, experts expected that its observations would confirm the Big Bang theory. Yet, just within 1 year of operation, the telescope amazed scientists with its extraordinary ability to peer into the universe's distant past. The JWST's groundbreaking capabilities have uncovered galaxies that date back to such an ancient period that they challenge the current understanding of the universe's origins. This discovery has sparked a wide debate about the possibility of pre-Big Bang matter. A major breakthrough came when cosmologist Rohan Natu, analyzing data from the telescope, identified a galaxy that existed shortly after the Big Bang, marking it as the most distant galaxy observed thus far. This discovery sent shockwaves through the scientific community, highlighting the remarkable capabilities of the James Webb Space Telescope. The vast potential of the JWST to alter our perception of the cosmos is just starting to unfold, with significant revelations about the universe's earliest stages. This period, loosely connected to prior cosmic events, holds the key to understanding the formation of the first stars and galaxies. The findings from the JWST have contradicted existing theories, revealing galaxies with features that defy previous expectations. This surge in the discovery of early galaxies has ignited a frenzy of scientific inquiry, urging experts to reconcile these new revelations with established theories. As scientists delve deeper into these findings, they are confronted with fundamental questions about the very essence of the universe and the forces that guided its evolution. In addition to the obvious advantages, the JWST is strategically positioned 1.5 million kilometers away from Earth, shielded from interference, and kept nearly at absolute zero by its sunshield, which is the size of a tennis court. This positioning allows the telescope to capture unimpeded observations of the universe, unburdened by Earth's atmosphere. Equipped with a massive primary mirror and sophisticated instruments, the JWST was specifically designed to uncover details about the early universe that were previously out of reach. This early cosmic era, referred to as the Great Dawn, began approximately 200 to 300 million years after the Big Bang, marking the point when the first stars and galaxies began to form. The mechanisms behind this process remain a key area of research, with various theories exploring the roles of dark matter, dark energy, and the interactions between gas and dust in star formation. The JWST's ability to observe galaxies from this critical period presents a unique opportunity for cosmologists to test their existing models of the universe. By studying these ancient galaxies, scientists can either validate current theories or discover gaps in their understanding that could lead to groundbreaking revelations. Initially, the JWST was expected to detect only a few faint, small galaxies during its early observations. However, the results far exceeded these expectations. The telescope's first images of the distant universe revealed an astonishing number of galaxies, with varying ages, sizes, and luminosities, far surpassing previous predictions. This unexpected influx of early galaxies has triggered a race among astronomers to redefine the record for the earliest known massive systems. New discoveries are constantly emerging, leaving even seasoned scientists in awe. Following the JWST's discoveries, both experts and the general public have been eager to explore the characteristics of these highly advanced early galaxies. Some theorists have suggested that potential errors in how the telescope interprets large-scale observations might account for some of these remarkable findings. However, the general consensus remains that these revelations represent a paradigm shift in our understanding of the early universe, offering an exciting glimpse into how much more we could learn. The recent discoveries of early galaxies made possible by the JWST have raised significant questions about the nature of the universe, challenging traditional cosmological models. While some researchers are investigating whether these discoveries can be integrated into existing theories, others suggest that these revelations may point to a far more complex and mysterious universe than we had previously thought. The critical question that remains is how the universe we know today emerged from the chaotic turmoil of its early stages. The JWST's early findings could drastically reshape our understanding of the Big Bang and provide new insights not only into distant galaxies and ancient cosmic structures, but also into the very makeup of our own Milky Way galaxy. As Mark McFadden, senior scientist for science and exploration at the European Space Agency, aptly put it, "You build these machines not to confirm theories, but to break them. You simply have no clue how it will break." The origins of the JWST trace back to 1985 at the Space Telescope Science Institute, STSCI, long before the launch of the Hubble Space Telescope. At that time, G. Weir, then the head of STSCI, was tasked with imagining what could come after Hubble. Despite early skepticism, Weir and a small team began laying the groundwork for what would eventually become the James Webb Space Telescope. Unlike Hubble, which primarily observes visible light, the JWST was designed to observe in the infrared spectrum, allowing it to peer deeper into the universe. This infrared capability is crucial for studying distant galaxies whose light has been stretched into the infrared due to the expansion of the universe, rendering them invisible to telescopes like Hubble. With its large, cold, star-like mirror, the JWST has become an indispensable tool for unlocking the mysteries of the Great Dawn. The need for such a telescope became apparent in 1995 when the Hubble Deep Field observation revealed a vast number of galaxies in what was previously considered an empty region of the sky. This discovery demonstrated the richness of the early universe and highlighted the necessity for a more powerful telescope capable of observing even deeper into the cosmos. After years of development and an investment of around $1 billion, the JWST was launched on December 25, 2021. By July 2022, it was ready to begin its critical year of scientific observations. Programs like the Early Release Science (ERS) and the General Observing Program were specifically designed to search for early galaxies. While initial expectations were modest, the results far exceeded these projections. The JWST's observations have already begun to challenge existing models of the early universe, uncovering galaxies that defy conventional cosmological assumptions. These extraordinary discoveries underscore the importance of pushing the boundaries of scientific exploration and highlight the remarkable capabilities of advanced technologies like the James Webb Space Telescope. As researchers continue to analyze the data from the JWST, new insights may emerge that further challenge and expand our understanding of the universe. When the first data from the JWST began arriving, cosmologists eagerly awaited the results. Many scientists had spent years preparing their data analysis systems for this moment. Instead of following the traditional peer review process, which can take months, researchers opted to share their findings on preprint servers such as AR14, where papers can be publicly accessed before undergoing peer review. This approach allowed for rapid feedback and discussions through online platforms like Twitter, where established scientists could quickly engage in dialogue about the findings. Rohan Natu referred to this new process as science by press release, and the ensuing surge of conversation was both intense and unprecedented. However, concerns arose about the potential drawbacks of this swift dissemination of results. Klaus Pontypool, a JWST project scientist at STSCI, cautioned that while the rapid sharing of findings enabled quick communication and discussion, it also risked overwhelming the scientific process. The accelerated spread of discoveries, especially in such a groundbreaking mission, introduced challenges to traditional scientific workflows. Despite the rapid pace of data release, the general consensus among most experts is that the current theory explaining the origins of the universe remains foundational for understanding the early stages of the cosmos. This theory postulates the formation of stars, planets, and eventually life, including human life, as an integral part of the universe's development. Despite the oddity of its name, the Big Bang theory offers a coherent explanation of the universe's beginnings. In its earliest stages, the universe existed as an extraordinarily dense point, far smaller than the tip of a pin, filled with tightly packed particles. From this incredibly compact state, a colossal release of matter and energy, the Big Bang unleashed the forces that would shape the universe. This massive event, occurring billions of years ago, set the course for the universe's unfolding story. As scientific knowledge evolves, however, inconsistencies have surfaced, challenging long-held assumptions. When NASA launched the James Webb Space Telescope, JWST, which is considered the most advanced and largest space observatory ever built, there was an expectation that its observations would provide confirmation of the Big Bang theory. Yet, in just 1 year of operation, the telescope stunned scientists with its unprecedented ability to peer far back into the universe's past. The JWST's extraordinary capabilities have uncovered galaxies dating back to an era so ancient that it forces scientists to reconsider what we know about the universe's formation. This revelation has triggered discussions about the possibility of pre-Big Bang matter. A major breakthrough was achieved when cosmologist Rohan Natu, analyzing data from the telescope, discovered a galaxy that formed shortly after the Big Bang, marking it as the most distant galaxy observed to date. This discovery sent shockwaves through the scientific community, underscoring the JWST's extraordinary power to deepen our understanding of the cosmos. The vast potential of the JWST to reshape our view of the universe is just beginning to unfold, offering significant insights into the earliest moments of cosmic history. This time period, which loosely aligns with previous cosmic theories, is essential for comprehending the origins of the first stars and galaxies. The discoveries made by the JWST have defied established models, revealing galaxies with characteristics that surpass prior expectations. This flood of early galaxies has prompted a wave of scientific investigation, pushing researchers to reconcile these new findings with existing theories. As scientists continue to analyze these findings, they are confronted with profound questions about the fundamental nature of the universe and the forces that guided its evolution. Beyond its impressive scientific contributions, the JWST's strategic positioning, 1.5 million kilometers from Earth, protected from interference, and cooled nearly to absolute zero by its sunshield the size of a tennis court, provides a unique advantage. This positioning enables the telescope to capture detailed observations of the universe without being affected by Earth's atmosphere. Equipped with a large primary mirror and advanced instruments, the JWST was specifically designed to capture unprecedented details about the early universe that were previously impossible to detect. This early period in cosmic history, known as the Great Dawn, occurred roughly 200 to 300 million years after the Big Bang and marks the time when the first stars and galaxies began to form. The mechanisms driving this process remain the subject of intense research, with various theories proposing the roles of dark matter, dark energy, and interactions between gas and dust in star formation. The ability of the JWST to observe galaxies from this critical era offers cosmologists a rare opportunity to test their models of the universe's early stages. By studying these ancient galaxies, scientists have the chance to either validate existing theories or uncover new gaps in our knowledge that could lead to major discoveries. When the JWST first started its observations, it was expected to detect only a few faint, small galaxies. However, the results far exceeded these predictions. The telescope's first images revealed a surprising abundance of galaxies, with varying ages, sizes, and luminosities, far surpassing what was anticipated. This unexpected flood of early galaxies has set off a race among astronomers to revise the records for the earliest known massive galaxies. New discoveries are being made regularly, leaving even the most experienced scientists in awe. Both experts and the public have become increasingly focused on the advanced features of these early galaxies. While some researchers have raised the possibility that the telescope's interpretation of large-scale observations might explain these surprising results, the prevailing view is that these discoveries represent a significant shift in how we understand the early universe, providing an exciting glimpse into the potential for future breakthroughs. The recent discoveries made by the JWST have posed significant questions about the nature of the universe, challenging long-standing assumptions in cosmological theory. While some experts are working to incorporate these findings into existing models, others suggest that they might represent the first indications of a much more complex and enigmatic universe than we had ever imagined. The pivotal question remains: How did the universe as we know it emerge from the chaotic and turbulent conditions of its early stages? The JWST's early discoveries could dramatically reshape our understanding of the Big Bang, offering new insights not only into distant galaxies and ancient cosmic structures, but also into the very nature of our own Milky Way galaxy. As Mark McFadden, senior scientist for science and exploration at the European Space Agency, said, "You build these machines not to confirm theories, but to break them. You simply have no clue how it will break." The origins of the JWST date back to 1985, when the Space Telescope Science Institute, STSCI, began laying the groundwork for a successor to the Hubble Space Telescope. At the time, G. Weir, the head of STSCI, was given the task of imagining what would come after Hubble. Despite initial doubts, Weir and a small team started planning for what would eventually become the James Webb Space Telescope. Unlike Hubble, which observes primarily in visible light, the JWST was specifically designed to observe in the infrared spectrum, allowing it to delve deeper into the universe. This infrared capability is essential for studying distant galaxies whose light has been stretched into the infrared by the expansion of the universe, making them invisible to telescopes like Hubble. Equipped with its large, cold, star-like mirror, the JWST has become an invaluable tool for unraveling the mysteries of the Great Dawn. The need for such a telescope became apparent in 1995, when the Hubble Deep Field observation revealed a large number of galaxies in a region of the sky previously thought to be empty. This discovery highlighted the richness of the early universe and underscored the need for a more powerful telescope capable of probing deeper into the cosmos. After years of development and an investment of around $1 billion, the JWST was successfully launched on December 25, 2021. By July 2022, it was ready to begin its most critical year of scientific observations. Programs like the Early Release Science (ERS) and General Observing Program were designed specifically to search for early galaxies. While initial expectations were modest, the results far exceeded these projections. The JWST's observations have already begun to challenge existing models of the early universe, unveiling galaxies that defy conventional cosmological assumptions. These groundbreaking discoveries underscore the importance of pushing the limits of scientific exploration and demonstrate the extraordinary capabilities of cutting-edge technologies like the James Webb Space Telescope. As researchers continue to analyze the data from the JWST, new insights may emerge that will expand and deepen our understanding of the universe. When the first data began to arrive from the JWST, cosmologists eagerly awaited the results. Many had spent years preparing their data analysis systems for this moment.